Okay, I think we can slowly start. It's a great pleasure to introduce Stefano Carrazza for the 12th session, I think, in our series of quantum computing and simulation. I'll pass it to Jose Ignacio to say a few more things about Stefano and his background, and then we will start. Jose.
Okay, can you hear me, Dimitris? Okay.
Yeah.
Well, I'm not kidding that it's a great pleasure for me to introduce Stefano Carrazza. I don't have his CV with me, but if I'm correct, Stefano, correct me, you had your master's degree with Arash, so in experimental physics. So you know how a laboratory looks, a good laboratory looks. But at some point you were attracted to high energy physics, and he joined the approach to have all the pattern distribution functions which are used at CERN from artificial intelligence approach from neural networks. And he became the head of all the technical development of these neural networks, pattern distribution functions. On top, he was also appointed as a fellow at CERN, and then he got, if I'm correct, in deep contact also with Monte Carlo techniques, and many of the simulation techniques, restrictive Boltzmann machines, and many of the techniques which are used in artificial intelligence. And when at some point we decided that we would like to have a full stack quantum computer in Barcelona, it was just natural for me to call for the help of Stefano Carrazza to lead the team of building all this stack of programming that goes from the entry point of the final user to the pulses that have to go to the quantum computer. And now Stefano is leading this project. He's leading the two projects, the technical project on neural networks, plus the project for the full stack quantum computer program, the full stack programmation of the quantum computer. And today, if I'm correct, Stefano, I'm missing something. You have done so many things. You are an expert in drones, you are an expert in apps, you are an expert in so many things that if anybody in the audience has any question about artificial intelligence, you have done 6 APIs, I think, 7 APIs. Well, he's an absolute professional. So now today he's talking about this stack of programming stack which is needed for a quantum computer, and I think this is very, very illustrative. It shows all the effort that is needed, and in particular he will talk about the very first level, which is the level of the entry point, a language which is to be compared to Qiskit or to CERN. Okay, if I'm correct.
Yes.
Okay, Stefano, please go ahead. And from now on, it's Dimitris, the boss.
Okay, thank you. So thank you very much for the invitation, and also thank you, Jose Ignacio, for the great presentation. It's a pleasure to be here and to present to you. So as Jose Ignacio said, I will do a slightly different talk setup. So you talk about, try to talk 20 minutes, 25 minutes with slides, and show you the idea of Qibo, the technology that we have encoded in Qibo, and then you move to a tutorial and try to show you in practice how to use Qibo, at least the basic features. No? So let's go for the introduction. And when we introduce Qibo, I would like to first just make a point about the technology. As you know, we are moving from CPUs to GPUs, and then getting even more application-specific hardware like FPGAs and ASICs, and finally, hopefully, using quantum chips for real-world applications and several applications. But this plot is not just a natural technological evolution, but is also, let's say, a map about the technology we can use for our current simulation. So we are trying to move from a general purpose device, the CPU, towards the GPU. And that was the main point when designing Qibo, and that you see in the next slide. So trying to make the classical simulation as fast as possible, based on the, let's say, closest general purpose device that we have, except than CPU. So try to use CPU and GPU in combination. Now, Qibo, as Jose Ignacio has pointed out, today is an open source API for the new quantum hardware that is under development by the collaboration between Barcelona and Abu Dhabi, the TII in Abu Dhabi. And as an open source full stack library, the idea is to have several layers, like the quantum hardware that will be in our laboratories, then a job scheduler for the quantum real hardware jobs, and then a client and server communication protocol. So when you build something like that, you absolutely need a language, or let's say a code framework that provide you the possibility to send information from the client to the server, receive the feedback from the server, and then make sure that the full pipeline works. So that's really the idea of Qibo. So Qibo today, if you try to design again the general middleware picture, is something that glues the quantum chip to a server queue and users. So it's the right side of this plot. And the idea is to have something that can prepare and execute quantum algorithms and provide access to the quantum chip as soon as you have the lab. So summarizing, when you build a middleware, you have something that in this slide I call ITS, the infrastructural setup. And this is something that will be in the laboratory, controlling the quantum chip, is the network of the quantum chip, and Qibo, which is everything else. So it contains the server queue, the client-server communication, and then algorithms for simulation that I will talk today. Now, the Qibo framework, as it was released a couple of weeks ago, is designed for simulation on classical hardware, taking consideration CPUs and GPUs, and it is prepared to execute the same kind of simulations in the real quantum hardware. So it is designed, the framework itself is designed by these 4 blocks. We have an abstraction layer, which is a genetic abstract representation of all components of our framework, like circuit gates, Hamiltonians. And this is completely arbitrary, so you don't have any specific implementation for these objects. They are just placeholders for backends. Then moving on, we have created a TensorFlow backend for simulation that takes into account the GPU hardware together with custom operators that I will explain in the next slides. So these are the 2 blocks, the 2 main engines of our simulation framework. On top of these 2 blocks, we have the quantum algorithms. As you see, the variational quantum eigensolver, QAOA, so everything that requires a specification is already there. And finally, the high-level API. So all the output, all the API, the classes, the objects that the user may use in order to prepare and execute the simulation. And in future, the real hardware execution. Now, the idea is to have something that is very flexible with a large code base of quantum algorithms and the possibility to mix classical and quantum algorithms together. Okay. So have a hybrid algorithms. The current release, so when we design a software, we have decided to generate 5 modules. So these modules are models. So in models, you find everything that concerns circuit allocation, annealer, and you see in the next slide the full features. Then you have another module for gates, callbacks, Hamiltonians, and solvers. So these are the 5 blocks. And when I'm showing this slide because every time you enter the Qibo framework, all the components that we require to do a simulation and in future circuit execution will be stored in one of these modules. Everything is there. In terms of features, Qibo implements two quantum processors. So the circuit-based quantum processor. So we do state wave function propagation, control of gates, measurements, density matrix, and treatment with noise, callbacks. So if you have to measure a quantity during time, it's there. Gate fusion. We have the distributed computation for using GPUs and multi-GPUs. And then the variational quantum eigensolver. So these are the main features for the circuit approach. Together with this approach, we have implemented the annealing perspective. So you have the time evolution of quantum states, the adiabatic evolution, and scheduling determination, throttle decomposition, and QAOA. So these are the main features that you can find in the current public release. In terms of technical aspects, as I said before, Qibo is designed with CPU, multi-threading CPU in mind. So it tries to use the full computational power that you have available in a single node. Currently, it is designed to work on a workstation. So if you have a powerful workstation with a good CPU, a multi-GPU setup, then you can really get the maximum performance from Qibo. And the only limitation you may observe is memory, depending on what you are doing, if you are simulating a large number of qubits. But other than that, the current setup is really optimized for a good workstation with multi-GPU setup. The design is really simple. In order to install Qibo, you can just do pip install Qibo and you get everything. And as you see later, there is a documentation, unit testing, continuous integration. So it's really a modern library with all the features required to make sure the code works. And you can find further information if you visit the main page, the Qibo.science webpage. Now, in terms of technicalities, the project was designed in Python with C++ extensions. So we have 10,000 of lines of code, 19% in Python, and the remaining lines are in C++. And the engine is based on TensorFlow 2. But that doesn't mean that if you grab TensorFlow 2 and you start doing your linear algebra operations, you get the same performance. Okay? Because TensorFlow 2 is designed for machine learning, and there are many features which are not ideal for quantum simulation. In particular, if you would like to perform linear algebra operations on huge tensors, large tensors for large number of qubits, you may see that the memory allocation of TensorFlow is not ideal. So for example, you cannot allocate more than 30 qubits because TensorFlow will have several copies of the data inside. So that's why we had to implement several custom operators in C++ to make sure the code is able to deal with large objects. And then everything else is based on standard Python objects like NumPy, SciPy, JobLib for the multi-GPU distribution. So everything is really packed there. There is no specific, no complicated way to install the code. So the code will be really straightforward to maintain and to use. Now let's go to some results, some benchmarks. So we do, first of all, circuit simulation, and as you know, the approach we implement is very similar to what CERN and Qiskit do. They implement the linear algebra approach, where you have gates, where you have the initial wave function, and then you do the propagation, and you see what happens after applying all the gates. No? And when we choose gates, there are several options, rotations, controlled phases, so it's really a combination of all that. Qibo implements all the main, most used gates that are available in other codes. And using that, you can, for example, build the simple quantum Fourier transform, which is our, let's say, candle for benchmark. And in
can
the
you see or hear, Stefano? Is it me?
I can see you, yeah.
Oh, sorry. I thought you froze for a moment. Maybe it's my side. No, go ahead. Go ahead. Sorry.
Okay, so you have the quantum Fourier transform. And well, when building the quantum Fourier transform, you use a couple of rotations, Hadamard and control not. So it's really something simple to encode. You know? And what we did for this first round of configurations, we took Qibo, which you see in this table is available in a single precision, double precision for multi-threading CPU, GPU, and multi-GPU in terms of hardware. And we compare it to several other libraries, in particular the ones from full stack providers. So you have CIRC from Google, TensorFlow Quantum, which is again an extension of TensorFlow, Qiskit from IBM, PyQuil from Rigetti, and Intel QS. So these are the libraries for real quantum full stack. And together with these 5 libraries, we added QC GPU and Culex, which are specialized on GPU, so a single GPU. One problem that we realized is that if you see the table, you see that the different frameworks, they decided to use different precisions and different hardware configurations. So it's sometimes is a little bit complicated to have an homogeneous configuration. All the numbers that you show now are based on an NVIDIA DGX workstation, which is a good machine with 4 NVIDIA Tesla V100 with 32 GB of RAM, and standard Intel Xeon E5 with 20 cores and 256 GB of RAM. So it's a good machine for, let's say, simulations up to 30, 33 qubits. That's the idea. So you have enough memory to hold the wave function of a state in double precision. Okay, so in terms of benchmarks, here you see on the left the quantum Fourier transform. So for the quantum Fourier transform in single precision, so complex 64, the total execution time for increasing number of qubits from 5 to, depending on the library and the configuration, up to 33 qubits. So let me just focus on Qibo to start with. So here you have in light blue the triangles, the performance of Qibo on CPU using single thread. So it's just a single thread, and this is what you get. So you get the pattern which goes up to a very large number of qubits, and it is quite compatible with the TensorFlow Quantum implementation, which is very similar. No? We use similar primitives and a single CPU thread, but you see that the TensorFlow Quantum stops at 30 qubits. And this is because TensorFlow cannot use more memory and you need custom operators. In our case, we had this implementation, so we can go beyond 30, and this is really limited by the machine memory that you have, not more by the code. Then you can look and compare these two curves to CIRC, and CIRC CPU is also very similar, but is slightly better on a large number of qubits. Now, if you take Qibo and you unlock the number of threads, so you just use the threads available in your machine, you get the rectangle in blue, and it is the line here below. So on CPU, it's quite good in a multi-threading environment. So it's the fastest algorithm in comparison to other libraries, including the QC GPU on CPU, which is multi-thread. But let's say the most interesting features of all these plots, on the right side you have a similar plot for double precision, is the performance on single GPU. So you see the dark blue circles, which are really very, very fast until reaching 31 qubits. So this is the maximum number of qubits that you can put in a GPU due to the memory limitation of the machine. But if you manage to do it, you get really fast results. So you can get a speed improvement of hundreds order of magnitudes compared to CPU. And then also in comparison to other GPU technologies, you can reach up to a factor 3. And here you see the ratio plot for QC GPU. Then the jump you see here, so from 31 to 32 and beyond, is because as we don't have enough memory on the GPU, we still can do the simulation because you can reuse the same GPU several times. So you do the calculation for a subset of your wave function, and then you take the different slices and you send the different slices several times. And even if you do that, the performance is not terrible. So you still get something faster than CPU, But obviously the asymptotic behavior has this small jump. Now you have this step function that moves it up. Now to solve this issue, instead of reusing the same hardware several times, if you have more than one GPU, you can take the multi-GPU setup. And this is what you see here with these rectangles in blue. So the code will try to use in this case, all the 4 GPUs in parallel, making the performance go down and getting the best we could using these devices.
Stefano, a quick question.
Sure.
To let you breathe as well. I don't see Qiskit on this one. Is it because it does not support 64?
Yeah, exactly. By default, it uses double precision.
Okay. So you can compare. Okay.
You can see it there on the right plot.
Right.
The purple curve.
Right.
There are a couple of other things. So it's really interesting this plotter to look at 2 features. No, the performance is interesting for sure, but also where the different curves stop. You see that this point here is just the last point you can use for Qiskit, because they have an NumPy implementation, and in NumPy the arrays, they have a hard-coded maximum value, so you cannot go beyond the 2 to the 32, 2 to the 31 in double precision. So that's really what happened when doing the benchmark. So before deciding what to do with Qibo, we did this benchmark, and when looking at these plots, we saw the different landscapes, the different providers, and we said, okay, we have to change a little bit of the technology in order to have a package that you can install in your machine. And if you have a good machine with good GPUs, you take the full performance on it. That was the idea. Okay, this is for the quantum Fourier transform, but we can do and see improvements in different circuits configurations. For example, if you take variational circuits, so you can take systems like the one presented here on the left, several rotations, and they have parameters. You may take the standard circuit and create a fusion of these blocks of 4 rotations, creating just a single qubit gate. So you replace all the 4 blocks with a unitary gate. And if you do that, you can measure again the performance, because now you can parallelize the evaluations of the different blocks of 4. And again, by doing the plot and comparing the performance, here we have a variational 5-layer in single precision on the left, and a 5-layer in double precision on the right. Again, you see that Qibo on GPU is very efficient and holds well on the low qubit regime and large qubit regime and in the 2 precisions. One point to notice, however, that you may realize is that here at the low qubit regime, so when I say low is let's say above 20, around 20, libraries written in C++, C code, or even Fortran can be slightly faster because there is no overhead when allocating objects. So, for example, Culex, which is written in C++, in this case, in this regime, is faster, and there isn't much we can do because it's language bounded. So if you need it, we can fix that by doing C++, but in general, as the performance is quite acceptable, we decided just to keep it simple and compatible with other Python libraries. So you see that there is a convergence of all of them at small regime. And concentrate on large regime, which is the most important one, if you wanted to have a large number of qubits. Okay, so this is for the variational circuit benchmark. Then, well, you can take the variational example before and then compare the precision, the performance between single precision and double precision on CPU and on GPU. So you see the big differences between these 2 pair of lines. So you have in red is double precision CPU, in green single precision CPU, and in these 2 curves here and down, orange is GPU in double precision, and blue GPU in single precision. First thing that we notice is the stopping point, and this is memory bounded, so that if you don't reuse the device, you can do one extra qubit by moving from single precision to double precision. And the gap between CPU and GPU is quite large. So if you do the ratio, you see that we have a performance deterioration up to a factor 2 for GPU when you move from single precision to double precision. But that only happens in the large qubits regime. If you are above 20, the performance is quite similar. And similarly on CPU, you have a well, less dramatic deterioration. So you can get a factor of 1.5 when using double precision, but again, only in the large number of qubits regime. If you do measurements, again, you can use a CPU or GPU. So here you have some measuring. The number of shots is in the x-axis and the total time is in the y-axis for different circuit sizes. So from 10 qubits to 30 qubits. In general, it scales quite good in CPU and also on GPU. The only big challenge here is memory again. So the GPU memory is limited, so you can get a very good performance for circuits up to 18 qubits. After that, the memory of your GPU is completely full. And what we do in Qibo is that we just move the jobs to CPU. So that's why you get similar performance for large circuits. But if you are in a regime with less than 18 qubits, you can get more shots without waiting for too long. So that's for measurements. And finally, concerning circuits, I wanted to show you this plot. So here we study the scaling of the time, for the evaluation time, as a function of large number of qubits from 25 to 33, using the different devices. So using single thread CPU, which is the first histogram in blue, to 10 threads CPU, 20, 40. So when you see this behavior, you can really see that getting more than one thread is very useful, because you can even drop by a factor 2 the computation, close to a factor 2. But after that, there is a saturation, and the performance doesn't improve a lot. And that's due to the communication, the memory and the hardware communication. You can't really get the maximum from all that because there is this overhead. Then comparing the CPU to single GPU, so the red histogram, you see an incredible improvement in comparison to single thread CPU. And this improvement keeps stable until reaching the memory limitation of your GPU. So in this case, when you go to 31, 32, and 33, we are reusing the GPU several times, and that makes the performance slightly worse. Now, if you have a multi-GPU setup, for smaller, let's say 25 up to 30, the performance is acceptable, and this, depending on where you are, close to CPU, and also useful. And it depends on, you see that the histogram bar is always below the CPU, but it really is strong, very strong when you go beyond the 31. So here you see reusing, using 2 multi-GPUs, you get faster results with single GPU, then with 4 even more, and then you can start reusing the devices to get the maximum performance. So that's really the best you can do when simulating large number of qubits. So this is in the large qubit regime. In the, let's say, small qubit regime, so if you look, for example, at 14, 15, 60 qubits, then the history completely changes, because it's preferable to use a smaller number of communications between the device and the memory. So here you see that single thread CPU and single GPU are usually very good for tiny circuits, so 14 and 15 are acceptable. Then when you go to 16, you need to use the GPU. So if you wanted to make some heuristics, this is the suggestion. If the circuit is tiny from 1 to 15 qubits, use single thread CPU. If it's 15 to 30, use single GPU. If it's more than 30, multi-GPU. So you have this suggestion when preparing your program. And all that you can configure and use directly on Qibo. So you can really decide what to do and which devices you'd like to use. Okay, and now my just last slides about the other processing mechanism that we have in Qibo, so the annealing. We have implemented time evolution. So we take the Hamiltonian. So you can select one of our pre-coded Hamiltonians, which are IZ models, the Heisenberg model, and many others. Or if you have your custom Hamiltonian, you just allocate it using our Qibo class. And it will automatically do the Schrödinger equation time evolution by trying to find the final state on so psi t for a fixed final time t. This is very good because you can take the time evolution and then couple it to some algorithm like the adiabatic quantum computation. So in this adiabatic approach, we would like to find the ground state of custom Hamiltonian, and we write it as the splitting of easy Hamiltonian, H0, and the hard Hamiltonian, H1. And we multiply this object by a scheduling function that will make the transition between H0 to H1 very smooth and adiabatic. No? So that's the idea. Qibo allows you to define H0, H1, and provide an external scheduling function, and he will take care of doing the time evolution and generating the energy, so computing the energy of your ground state, so getting it automatically. So here you have an example. If you take the Pauli matrix, so the H0 as the X1, X's, and the X1, in this case is an easy Hamiltonian, so it's an Ising model, but it's an easy system, so we know the solution. If you put these two things together and you do the time evolution, you can monitor, for example, the ground state energy of H1 during the time evolution. So you see that it's slowly going down to the ground state, to the expected ground state, and that is performed automatically, and in this case using a linear schedule. Now this particular algorithm is quite useful because it is something really connected to the hardware. So if you manage to understand the scheduler function, what is the best scheduler function and what is the best final time for your evolution, you can provide these parameters to your computer, to your quantum hardware, and get the prediction for your custom Hamiltonian. So what Qibo does is exactly this procedure. It minimizes the scheduler function if you want to, and provides you the shape, the final shape of the scheduling, and the best final time for the simulation. And these parameters can be really used and sent to the quantum hardware. And just before showing the full scheduling configuration, just one comment about the techniques we use to simulate time evolution. So we use two technologies. The first is the trivial one based on ordinary differential equations. So we take our Hamiltonian, we do the exponential operator, and then we solve it analytically, trying to use using linear algebra and the differential equation algorithms. Now you can use Runge-Kutta if you prefer an approximate and fast solution, or the direct exponentiation of your Hamiltonian. So that's one possibility. That particular possibility is interesting, but memory bound. Because if you consider the exponentiation of a large Hamiltonian, which depends on the number of qubits, you are memory bound. So to avoid that, we have also trotter decomposition built in. So you can convert your Hamiltonian representation in a trotter representation, and then you convert the problem into a circuit. And the circuit has lots of advantages, in particular the memory. So I am now showing, let me show some numbers so you understand exactly what I'm talking about. So here I do IZ model adiabatic evolution for a fixed number of parameters. And with the solid lines, you have the direct exponentiation of your Hamiltonian. So you see that the time grows quite fast, and we are memory bound. So we cannot go beyond, even if you use the CPU with a lot of memory, you get stuck at 15 qubits. There is a small improvement by moving from exponential solution to Runge-Kutta in terms of speed. but you cannot really do more than a limited amount of qubits. Now, if you project that into a trotter decomposition, then the performance really is improved a lot, and you can go really beyond 30 qubits, and the behavior is quite similar to a standard circuit, like the QFT example. You can do up to 33 qubits, and there is no more memory limitations, and also the speed is quite good. So that's the two possibilities you have. Or you do an exact solution with exponentiation, or you do the projection into a trotter base, and you go for the circuit representation. Moreover, the trotter representation is quite nice if you have a hardware which do not support annealing, directly annealing. So if you have just a quantum circuit configuration in your laboratory, that approach will be really good, because you can prepare your state and send it to the computer. Finally, last slide about the adiabatic evolution. Here, what we do is that we try to tune the scheduling function, in this case ST over T. We take a polynomial prototype function and then ask Qibo to model this scheduling in order to achieve the ground state of our IZ model. So in this top left plot, you have the final scheduling function, so how it looks like. So it's not linear, it's slightly, it has this bump and then goes up. On the right side, you have the energy of ground state during the interactions of our optimizer. So the optimizer is trying to understand what's the best scheduling function and final evolution time. So you have sometimes some jumps, but it's going down after some interactions. And then in the second row, you see the evolution of our Hamiltonian and the overlap with the right solution, with the good solution. Yeah, so this feature you can use it and apply it to any other Hamiltonian that you may have. And you can decide the parameterization for your scheduling function. Okay, and finally, just to let you know, Qibo provides these functionalities, but we have also a very interesting code base of tutorials with real applications from variational circuits. So we have here several examples from papers and coded with really a tutorial where you can read and follow the instructions with code and physics explanation. Then we have Grover's algorithm and adiabatic evolutions. So we have these 3 blocks of examples, plus quantum singular value decomposition and quantum unitary approach for finance exams. So we're really covering physics examples and beyond with that. And everything is in the documentation link that you see here, and they will show you in the next. Okay, so I go to the conclusion. So Qibo was designed for efficiency, but having in mind the possibility to control in the near future the quantum hardware and submit jobs. Here we have a table with the current models which are encoded in Qibo, so circuits, distributed circuits for multi-GPU approach, the quantum Fourier transform, the variational quantum eigensolver, and the quantum approximate optimization algorithm. And together with these objects, we have the annealing approach, which is the state evolution, and the adiabatic evolution. And that's, let's say, the first release. And we are planning for the next month, the next, let's say, in short, by the end of this year, probably to have more algorithms and more features from that can be useful for research in general. Okay, so I would like to stop here about the slides, and then I move to the tutorial. Maybe if you have questions about the slides, may ask.
Yes, please, people, we're kind of a smaller group today. Unmute your mics, introduce yourselves, and ask if you want. No need to go via me if you have any questions. Or you can ask at the end. Any questions?
Hello, I'm Jonathan. I'm a student at CQT right now.
Okay.
I was just curious, when you compare Qibo to CirQ, did you only compare the time taken? Do you also compare like the resource allocation, like RAM resource allocation?
Mm-hmm. Yeah. Yes. Yeah, so everything, we tried to make sure all the implementations for each provider are, let's say, the best suggested by them. No? And we use this as a reference to boost the performance. So during the development, we discovered some points where Qibo were not optimal, and then we look at it and debug it and try to make it slightly faster by tuning the configuration, by creating custom operators in C++, and so on and so forth.
I see. Thank you.
Thank you. Okay. Yeah. Other questions? If not, we can move to the tutorial and then.
Yeah, please go ahead. Yeah.
Okay. Okay. So let me share my other screen. I think should be this one. Okay. Can you see?
Yep.
Can you see my screen?
Yep.
Okay. So here you have the Qibo GitHub webpage. So you can find all the documentation, the links for the examples, everything there, and to the instructions to install the code. Together with this GitHub webpage, we provide read the docs documentation, very similar to other frameworks. So you can just go there. There are several entries, sections from basic examples to advanced examples and application tutorials. So as I said before, if you wanted to do some, for example, VQE, you can look at this link here. And here you have the problem overview, the solution of this problem, the link to the paper, link to the code, and some code that will allow you to run the example and get the results, and some explanation about what you get from that. So that was the idea, to build a code base with examples that can be used for other applications or as a template for new applications. Now let's move to the tutorial. So is Python. So in principle, if you have a Jupyter notebook or a Google Colab, it will work well. So the first thing to do if you are in a Google Colab environment is to do this pip install Qibo. And after that, you can just check. So for example, here I'm checking the versions of my code, but that's not really necessary. I can import a TensorFlow, I can check the versions of my Python system, the TensorFlow version and the Qibo version. The thing which is important is here. So the imports required when you use Qibo, at least for the circuit and the annealer, are the ones you see here. So I do from Qibo, I import these four modules. So the callbacks, gates, models, and Hamiltonians. So that's why I show you in the first slides of my talk, the 5 big modules. Now, with these 4 or 5, depending what you do, you have everything. So you can really start coding and generate almost 99% of the examples. Now and then here I just set up matplotlib to make a nice plots, and let's move to the quantum circuits. So supposing you'd like to do something like that, so you have a 2-qubit circuit starting at the ground state and applying a Hadamard for each one. So what we do is very simple. You take circuit, you create a variable circuit, and then you do models dot circuit, and this is the object that will hold and create the Qibo circuit. The parameter you see here is the number of qubits. In this case is 2. Then to add the different gates, you just do circuit add gate, in this case gates.h, because you want Hadamard, apply the 2 qubit 0. And then you repeat it again for the qubit 1. Okay. So this is enough to generate a circuit, and you are ready to do the simulation. So for example, the simulation can be achieved by taking the circuit and then putting the brackets. So you just, it's like a function. So you run this function and you retrieve the final state. So here you see the output from this calculation. So very, very simple. And also, if you look at this, you see that it's familiar with other frameworks, because in fact, there is no, we are not inventing the full interface. Now, we would like to make it very friendly and very easy also to convert from one to another library.
This is like Qiskit, right? It looks like
Very,
Qiskit.
very similar. Yeah, very similar to Qiskit. There are some differences, and you see in the next, but that's the idea, to keep it simple if you needed to translate. But instead of translating, and that's important, I can show you, I think I can show you it already. For example, if you wanted to do something a little bit more complicated, like this circuit here, you allocate, as usual, the circuit, and well, you can use the different gates, measurement gates, registers. But then there is this nice feature of circuit to Cosmos. And when you do circuit to Cosmos, you get a piece of code that can be really sent to other libraries.
And say, put it to.
Yeah. So you can put it in eventually you can even change backend or middleware eventually by putting this thing up. So it's designed to provide you this simplicity and facility to move from one language to another. Okay. But on the other hand, you may ask now, well, why, if you do something like that, why you didn't took or forked Circ or Qiskit and then try to implement your stuff based on that? Well, for two reasons. Now, first is performance, because you know that the simulation performance is not ideal. And second, because as you have the hardware and you have the access for the full stack, it's much better to have full control of all the different primitives. So you can adjust the code as you need it, based on the configuration.
You own what you write.
Yeah, exactly.
Yes.
It's much easier to maintain, and you know, it's a different thing. You cannot, you do not, for example, even if you depend on things like TensorFlow, TensorFlow is okay, but during the development we found several bugs, and we had to fix these bugs in TensorFlow and report them to the guys. And it's okay, but it can be also limitation depending on the manpower you have available.
What is the license? I guess we can discuss this at the end. What is the license you guys released this under?
It's Apache 2, so it's completely open source. You can do almost whatever you want with this code. Okay. It's very, very, very broad. Okay, then just before moving and showing in practice, there are functions like circuit.summary that prints the current circuit depth, total number of gates, so you have a summary of your circuit. And there are many facilities. So obviously you could code your quantum Fourier transform manually. There is no problem at all in doing that. But we provide already a pre-coded model. So if you do models.qft with 4 qubits, you get automatically the plot you see in here. And then if you do again a QFT and use brackets, you have the final wave function for your circuit computed. Again, also here in this context, you can do the dot summary, and you get again the circuit depth, the total number of gates, qubits, and so on and so forth. So let me move to the Google Colab. So if you are familiar with Colab, I can just create a new notebook. So it creates, allocates a new machine for me. Okay, so I'm now in a new machine. As probably you know, Colab is designed for machine learning. So if I go to runtime, this is valid for everybody, so you don't have to pay anything. If you go to change runtime type, you have this combo box, and in this box you can select the GPU. So if you do that and save, in principle, if I'm lucky, I should get a good GPU. Let me see. So if you do NVIDIA SMI, we should just wait a couple of seconds, and it will tell us the hardware we are running. So it's connecting to the machine, and here you go. So I got a Tesla K80, which is, okay, not spectacular as machine, but sufficient for a simple simulation, in particular because the memory is very large. So you have 12 gigabytes of memory, it's very close to 12. So now, okay, I'm in this Google Colab. I don't have Qibo because it's a new notebook. So I do !, pip install Qibo in this way. And then I do Shift Enter to evaluate. So now the code is looking to the server, the PyPy server, and download the Qibo with all the dependencies. Yeah? So it did all the thing for us here. So now I can, for example, try to import Qibo. Import Qibo. Yeah, so he has imported Qibo. And if I do, so the first thing we can check is the version. So if I do Qibo.version, you see 010, which is the latest version we have public. And now let's try to do some benchmark. No, let me try to do a quantum Fourier transform for 25 qubits. So if I do time, and then I go, say, from Qibo dot models, import the QFT. Okay, very simple. Now we have already everything pre-coded. Now I can allocate my circuit by doing C equal to QFT. And let's do 25 qubits. So this should not take much time. Final steps to compute the final state. So ask the code to execute the circuit. So C brackets and execute it. So as you can see, it took just 1 second and 17. So it's pretty fast. And using the GPU. If you try to do the same simulation on a CPU, you should see something like 25 seconds, 30 seconds, depending on the machine you have. So already here you get a very good performance. If you wanted to query the final state, we do C dot final state. And you see that the numbers, yeah, so these numbers are correct. Here you have the result, the shape of the result. So this is the size of your wave function. So it's 2 to the 25. Is a double precision simulation. And these are the numbers in the state. And let me show you, okay, I did everything with the QFT class, but in principle, I can do exactly everything manually. So for example, I can do from, I can repeat the example by doing from Qibo, import models and gates. And you also use NumPy, import NumPy as NP. And if I wanted to reproduce exactly what I did before, I do, for example, number of qubits, let's say 25. Then I do a circuit allocation. So circuit models dot circuit with qubits. So that's very, very, very simple. And now I do the QFT manually. So I do a for loop in the range of qubits. And for each qubit, I will append to the circuit object from the gates class, the Hadamard, followed by another for loop in the range of qubits from E1 plus 1 to n qubits. And here I will create the angle of my control Z gate. So the theta will be in this case pi over 2 squared, so to the power of I2 minus I1. And finally I do circuit add gates CZ pole, which is the control gate rotation over Z in the blocks here, E2, E1 and theta. And in principle, that's it. So now I have a nice circuit. So if I do time and I try to execute this circuit, it should give me exactly. So it did the time is very similar to the previous one. It's 1 second. And the final tensor is exactly the same as before. Okay. So just that, you see, we provide some models which are already pre-coded. Everything else is very simple to code. It's just append the gates and you get the result. Okay, final thing, because I don't want to move. I mean, I'm already 40 minutes. But last thing I wanted to show is the measurements. So if you, because it's probably something useful for many of you, the measurement gates are gates. So if you have something like this circuit, you have just to append at the end of your circuit the M0, M1, and then perform shots. When you do circuit n shots and you pass the number of shots, there are two possibilities to project the data, or in the binary basis. So you get the different combinations, and you can from that generate a histogram, or if you want the histogram, just do shots, frequencies, and you have the counter for the different state configurations and the number of shots. If you take one of these two prescriptions, then you can make your histogram and get the measurements. Okay, there are many other things that I cannot cover in this time, but just to make you sure, you know, switching precision using multi-GPU is really something possible to do and very easy. And the documentation really goes in all details explaining how to do the thing, the configurations, how to prepare the circuit, how to execute it. On both regimes, on circuit regimes and also on adiabatic evolution regimes. Okay, so probably we'll stop here. So thank you very much for your attention.
Okay, thank you very much, Stefano. It's very interesting. Questions, comments? Just unmute yourself, say your names, where you're from, which place you work, and ask the question if you have any.
Hi, I have a question.
Yep.
I'm Benjamin from Prof. Dimitri's group at CQT. So my question is, if you use the same like backend, let's say if I use Qibo, for example, and I want to use the same backend as something like from Qiskit, the speed up comes from, like, will there still be a speed up? The speed up that is being gained from this is the speed up in the overhead of Qibo is, I think, what I'm asking.
Well, the point is this: if you use Qiskit circuit, you are using their implementation, so their simulation engine, which is based on different technology. For example, one can use NumPy, the other can use a plugin to Culax. I mean, it's very the thing is complicated. No? Depends on what you set up. Here, what we did is that we tried to use TensorFlow for the engine with a very precise custom operation definition. So you can take TensorFlow as it is, and it will provide some performance for you, like in the TensorFlow Quantum library, TensorFlow Quantum. But what we did is that we took all the different custom operators, we modified the way to apply gate multiplication. So instead of just multiplying the gates to the wave function, we look at the gate configuration. And if this gate is sparse, for example, we do not multiply zeros by the wave function. And this is something that happens in other libraries. For example, TensorFlow do not look at these features. It just multiplies and that's it. So we try to modify for each special gate the algorithm that is used and the way to distribute the computation across threads. Now, so if you have threads on CPU, the distribution is based on the size of your wave function. If you move to GPU, you look at the number of threads available and blocks available in your device and use that. So it's a mixture between what TensorFlow provides and several custom operators in C++ that take care of making all these operations as fast as possible. So it's not possible to, let's say, couple that engine on Qiskit directly. So you have, for example, to export the code from Qasm and then import in Qibo, and you get the performance from Qibo. So ideally, the setup is if you have already everything on Qiskit, well, and if you don't have time or you don't want to convert it into Qibo, just take the Qiskit, export into Qasm, and import the Qasm in Qibo, and then you can do the simulation taking all these the features that I presented.
I see. Thank you very much.
Thank you, Ben. Good question. Anybody else? Anything else? Great. Well, it's very nice. I think at least some of us will definitely give it a go. It's good to have something. Now, I have one question, actually. You mentioned it earlier. So this is all Python with a little bit of C++. I guess if you change the mixture, did you consider changing the mixture, doing a bit more low-level languages, more C++? We give you a bit more flexibility, more space in some cases, or how come you decided the mixture at this?
Yeah, that's a very good question. Let's say we decided to use this approach, a Pythonic approach with libraries that provide you, like for example, TensorFlow. You can ask why you decided to do TensorFlow and all that. Well, it's not for sure. It's not a question of knowledge. So in principle, we could do exactly the same by doing by implementing the code directly using CUDA, or because indeed this is what we do. So the C++ we have is CUDA code, is C code. But you should consider the usability. For example, I have just opened the Colab notebook, and I managed to run the simulation on GPU without having to deal with CUDA drivers, CUDA compiler, any kind of things like that. So the other libraries, for example, the ones that some of the ones that I show you, in order to install them in the current system is already let's say a nightmare, because you have to check all that to make sure that everything works, and then finally run the code. So you probably waste something like a half an hour minimum to get it working well. And that's the point. Now, if you want something, if you want something simple and easy to maintain, then you have to decide to go slightly lower level for the interface, but making sure the engine and the computation is compiled and fast. The custom operators, for example, all these features that accelerate Qibo are compiled, and we are compiling. But we had so when we distribute the PIP packages, we are pre-compiling the custom operators for different targets and making sure it works with TensorFlow for different platforms, from Macintosh to Linux, and for different Python versions and compiled versions. And all that is already a complicated task, because you have to test all that. And that's why I say we prefer to do this approach, because then it's easier to maintain, and also for the user in general should be simple.
Good.
Yeah. Now, if you need C++, if you need to link this code to C++, is also possible. That's an important point to remind.
Very good. Thank you very much. Any other points, connections?
Yeah, sorry, I just have one more question.
Yep.
Yeah.
Is this optimized for NVIDIA GPUs only?
This is optimized for, so the custom operators are CUDA, are written in CUDA. So you must have a NVIDIA GPU. But we provide internally two different backends. So the custom operators, which are the one I show you, and the default TensorFlow. So if you have an AMD and what's the name, the Radeon. No, if you have a Radeon GPU, you can install TensorFlow Rock M, which is the special version for these machines, and then Qibo can run on the Radeon GPU. Okay. The only problem that you may notice is that performance. So even if you buy a Radeon 7 with the Sapphire, so one of the best Radeons, you see that the performance is not so great for the kind of operations we are doing in comparison to the equivalent on NVIDIA.
Understand. Thank you.
Okay. All right. So if there are no more questions, let's thank Stefano again. Virtual clap from far away. Thank you for waking up early in Italy and guiding us to the universe of Qibo. And the talk would be released on the website soon. And thank you everybody for joining.